is complete. All right. Good morning, everyone. Welcome in our 33 Athena seminar talks for this semester. This is the last but not least, as we said with John and the rest of the people. I would like to thank you, all the participants, for your participation, and I'm looking forward to your engagement with our speaker after his contribution. So I will speak a bit about Professor John Xiaogangxi. I'm sorry if my accent is not the perfect one. A few things about John. He has received his PhD from the University of Washington in Seattle, USA. Now he's an associate professor in hydrology in the University of Glasgow, one of the most, I think, historical ones in UK. Definitely in Scotland. He's an associate professor in hydrology, and his research interest obviously involves hydrology and water resources. His research has received more than 1,700 citations, and today John is going to speak to us about a question. I think that his title is a question: does AI offer solution for hydroclimatic extremes? And I will say, while AI is not a substitute for physical understanding, it significantly enhances hydroclimatic resilience when integrated within domain knowledge, high quality data, and sound policy frameworks. At least, as a short introduction for you, John, I would like to thank you on behalf of the organization committee of the Athena Talks. Thank you very much, and the floor is yours.
Okay, thank you so much, Costas. And so first of all, let me share my screen and make sure you can see this very well. So can you say, well, from your side? Costas, can you confirm this?
Yes, sir. It's very fine.
Okay, that's great. So good morning, everyone. It's my great pleasure to deliver this talk through this Athena talk and also titled with like, does AI offer solutions for hydroclimatic extremes? So, first of all, forgive my voice. It's not perfect. I was hit by a cold last week, so still have some aftershocks. So, here I use the question mark for this title for two reasons. Firstly, in terms of AI definitely is very popular right now. Everyone is trying to apply AI in their subject areas, especially hydrology. It's many people trying to use AI, develop different AI-driven models, but I think unfortunately it's still not fully recognized by the community, especially hydrological modeling community. So the second reason I use the question mark because I want to ask this question to the audience today. And hopefully after my presentation through the Q&A session, we can have very good exchange on this topic. And this also from my side, I really want to hear your thoughts, your voice on this topic. And as routine, basically for my talk, first of all, I would give you some background introduction. Especially through this opportunity, I want to share briefly share my research interests and also the current major research directions in my research lab. And the second part, I would like to just show you, traditional hydrological models and what's their challenges in the current traditional distributed hydrological models, and also through a case study, and to show you what are they, and also what the bottlenecks, why we cannot overcome this in a short time frame. And the second part, through I want to share two case studies, basically using AI-driven models, currently ongoing research in my research team, and through the comparisons with traditional hydrological models, we can say what's the advantages, what's the limitations, and then in the end, so there are some take-home message, and also I'd like to raise this discussion with all of you. So again, this is basically my background, and currently I'm a senior lecturer in hydrology and climate in the School of Social and Environmental Sustainability. And this is basically a equivalent title and associate professor in your university. And also, I'm the director of research in the school and program director for the MSc Environmental Science. Okay. So I guess probably some of you may see this slide before. I borrow this from the CRED report. Every year they update this report and seems this is aged report published in 2020. I like this slide because they have this good statistics showing the occurrences in the last 20 years. Basically, they starting from 2000 to 2019. So clearly you can say, different categories of natural hazards, including flooding, storms, their percentages, and also including droughts. They're all water-related natural disasters. Here I also include the landslide because 80% landslides, they were triggered by heavy precipitation. So given that there are more than 80% natural disasters, they are water related. So that's why the motivation of my research is to investigate how climate and human-induced environmental change is related to land surface hydrological processes, and also what these relationships portend for human needs. So currently in my research lab, there are four research directions, mainly including hydrological modeling, development, and enhancement, and also focus on the mechanisms, the physical processes in terms of climate extremes and water hazards, mostly focusing on floods and droughts. And water resource management, once we set up the modeling, we can do a lot of meaningful uh, for the practice side. So this is basically to improve our water resource management, AI and remote sensing. General speaking, they are very useful tools, can offer powerful and also very useful data sets for us to drive hydrological models. And also now data-driven model, it turns out another pathway for us to improve forgive me, so to improve our practice. So the first research direction, actually, by training, I'm a modeler. I'm familiar with more than 7 hydrological models. And wake model, here I want to take this as example because during my PhD, during the whole period, I worked with wake and working with Professor Dennis Latimer at the University of Washington. So during my PhD, I did model coupling with MOCON. This is basically for auto calibration for the wake model. And also right now, some of my PhD students, they continue to work on this and trying to enhance the model using different schemes and modules. And so in terms of climate extremes and water hazards, in terms of this research direction, we did quite a lot of work, and this is a focus on different parts of the world. So some is related to high Arctic in Canada, and also some parts of China, and especially focusing on both floods and droughts. And once we set up this modeling or develop some useful tools, we can apply this for the water resource practice. For example, this is one project with working with some colleagues in China, and we try to split the climate and human-induced impacts on the hydrological regions. And for the river catchment, this is for the uh, Pearl River Commission. And also we develop some useful tools, and this is based on different students' theses or dissertations, and work on the catchment scale or urban scale. Basically, this to have comprehensive flood risk assessments, and this help us to improve the flood resilience for the water catchment basin scale or the urban scale. And AI and remote sensing, basically, they are very useful. We have done some research projects, for example, trying to make very high resolution snow depth data because once we have these UAV observations, we have like 10 by 10 centimeter observations and trying to improve the large satellite-based data size, get very high resolution snow depth data. And also some of my PhD students, one student from the UAE, trying to use GRACE data to have good estimation for groundwater and surface water, although surface water is really minor part. And the storage changes through GRACE and also machine learning approaches and for his home country. And this is a very important irrigation area in the UAE. This project, it has generated some impacts, because it has been acknowledged by the UAE government environmental department, and this can be very generate a benchmark research for their practice. Okay, so now let's move back to the topic today. And so here I want to show you two review papers, although they are kind of like out of date, but still very useful. So the paper published in 2022 showing that just for the flood mapping, you can say in terms of number of papers, starting from 2010 to 2021, there is significant increase. And also in terms of the model comparison between physics and data-driven models, and some data-driven models, they show great advantages in terms of this evaluation metrics. So basically, according to these review papers and previous research, it has raised a great interest in academia, and not only in academia, and also industry. Some Huawei, as a giant IT company from China, they have released this basically the game changer product. I believe this is the first weather focusing product based on machine learning. It's called the Pangu weather focusing model. So in terms of their technical report, they're not only promising for the global metrics, especially for the extreme events. I think this is basically the major focus for my research, right? I care about more climate extremes and water hazards. So after 3 months, this is in November 2023, Google they released the GraphCast. So they claim this basically the most accurate 10-day global weather focusing system, and still they are keep updating this system using their Google system, because they have huge resources and capacity on this. So the Europe is trying to catch up. So just February this year, and ECMWF, they released this new AI system for weather focusing, and also claim that this system can do a very good job for up to 15 days ahead. So I checked their technical report. I found, okay, 15 days, basically, that's mainly for temperature focusing. But for precipitation and wind speed, it's almost like 6 or 7 days. But still, this is a big step for AI weather focusing model, and they have this global coverage. Uh, Before the pandemic, actually starting from 2018, Google they have this initiative they call the Flood Focusing Initiative, and trying to build up this global flood focusing system using AI-driven models. So now you can basically have the access to their Flood Hub webpage, and to say basically they have large coverage more than 80 countries and covering more than 460 million people. This is huge, right? So I think this platform is still they still make this, improving this, also trying to expand the coverage. So I think definitely it's a great opportunity to work with Google flood focusing initiative team and trying to, help them. And I mean, this help actually, this is like a co-developer, co-sharing these techniques and to move this forward. So next part, I would like to focus on just introduce the development of the physical-based hydrological models. And through this process, I would like to share one case study. And all this actually is not focusing on the detailed research outcomes. Instead, we want to focus on what's the major challenges in the current traditional hydrological models and why we cannot figure this out in a short time frame. So I would like to use wake as one example. And because currently wake is very popular, wake model actually is co-developed by the University of Washington and Princeton University. So at the time, we really need a land surface scheme. This is basically back to 1990s. So we really need a land surface scheme basically to couple with global climate model. So I think this is basically the major motivation why Dennis and Eric they try to develop this land surface scheme. And it's not just like previously hydrological model for flood forecasting or for water supply purpose. So that's why it has both water and energy balance and covering more features, physical features on the land surface. And at the time, given the limitation of computing facilities, so it's grid cell based. So this kind of like nowadays it kind of turns out a dilemma because this I think this at the time definitely it's a very wise decision. And also it can do online or offline simulation depending on coupling with GCM or not. And so the grid cell based, the major feature, during the model runs, the neighboring grid cell, they cannot talk with each other. So that's why when you set up with model, you need to really pay attention to all these assumptions. This is basically, otherwise, probably you may screw up the whole model setup. And so just pay attention for this grid cell based modeling and always vertical fluxes, they're much larger than horizontal fluxes. And also there are some land surface features like lakes, wetlands, or even reservoirs. They cannot have large significant channel inflows. And also over bank flooding is not significant. Otherwise, we cannot cover this inflow. So and also in terms of the grid cell size, the size of the grid cell. So we basically have these suggestions. It could be from 1 kilometer to large coverage, 200 kilometer by 200. So for traditional hydrological models, we always have this, we have to face with this scale issues because this is basically the issue, the normal issue in surface hydrology. And for example, and for the land surface conditions as shown in this picture, right? How to present this properly when you set up these grid cell models and what's the best suitable solutions you need to consider or identify in terms of original data sources you may have the access. So given that, probably before setting up all these physical-based hydrological models, you need to consider what's the best spatial and temporal solutions for them. And it's really up to the research questions. For example, if as shown in this figure, if you want to focus on, for example, the flooding study, right? The flooding issues. So like number 4. So its best temporal resolution we suggest is from basically daily. Definitely, it's better to go for sub-daily, but still, at least starting from daily to weekly or annual. And for the spatial skills, you at least need to cover subcatchment, right? Because this could be the minor unit you need to cover, and also up to regional or even it doesn't matter, right? For grid cell based, it could be up to continental scale or global scales. Uh, but for other research questions, for example, if you want to focus on biodiversity study, as one of my friends working on this, and sometimes they did the simulation for uh, several decades or even several centuries. So this is hard to believe, in our research. Usually we did some modeling experiments for several decades. That's long enough, right? And it's really up to the data availability as well. And also, in terms of spatial scale, you do need to consider larger spatial scale to consider the overall change of biodiversity, and probably not for a minor like subcatchment scale, right? So another issue, I think this basically is also related to the model structures, because these different model structures, they are based on different these assumptions, right? As we show for the grid cell based, there are many assumptions in terms of this model structure. And if you want to do something research, use the model, especially focusing on the impacts of soil moisture on crop growth. If you set up this model in 1 centimeter scale, and meanwhile, it's really hard challenge to upscale this to the kilometer scale, because all these assumptions probably it won't work if you scale up to larger spatial scales. So this is basically the major bottleneck. That's why we have different hydrological models. And even in our research team, previously at the University of Washington, we have two physical land surface models. One is wake to cover the spatial scale from 1 kilometer to 200 kilometers. But another model called DHSVM that can cover really finer spatial scales, spatial resolutions. So also for the model runs, because you need to cover basically sometimes to different parts of the world, right? So we have to consider the land surface features, conditions. For example, the cold region hydrology features like snow, because this in some parts of the world, snow-dominated regions, this can be significant in terms of the water contribution to the streamflow, right? So this map actually I borrowed from a Nature paper published in 2005, and showing that spatial global coverage of snow-dominated regions. So based on this, probably we do need a snow model. And so for week, we have a two-layer energy and mass balance snow model. This is developed by my friend and colleague, and also Costas, originally from Greece. And also, we do need some other model schemes and modules to cover other snow behaviors like blowing snow, like canopy snow, interceptions, or some other cold region hydrology features like frozen soils, right? So this all the modules we need to add on this is land surface hydrological schemes, and lakes, white lines, and even others, So because Wake is an open source the platform, so that's why right now you can find different version Wake models, because people want to uh, and enhance the Wake model with their based on their research. For example, they can put on irrigation and reservoir scheme, or carbon cycle dynamics and dynamic crops. Or definitely you can put this based on developer NA schemes based on your own research. So here I want to say, the traditional hydrological models, and it turns out in the end, you may say a large model schemes, right? With different components. So in terms of the and model simulation uncertainties, so large part of uncertainty is can be resulted from this complicated model structures, right? In addition to the model parameters, or the input data, uh, basically generated from the field measurements. So next, through case study, this case study is not focusing on the or scientific findings. Basically, through this process, I want to show you what's the issue using the current physical-based hydrological models. So this case study is use the river catchment regions from the Western Canada, and this is basically called the Fraser River Basin. We set up this model for the his historical period. Basically, this is based on the field measurement data, and also for future projections. We want to say through this model runs whether or not we can say the future projection was the physical changes, and it could be make, and doesn't it make sense or not. So through this model, we can, after the uh, surface surface the runoff generation, we can set up this model using the routing part, because in Wake, basically, this is the two fundamental components, and runoff generation and routing process. And after that, we need to calibrate this model based on the field observations, right? This is basically a routine process for the model application. So in terms of model calibration, this is basically the calibration results for the Fraser River catchment. And the black line, this is basically from, we call it observations, basically from the field measurements at the gauge stations at the Hope. This gauge stations at Hope, which is a small city. I have been there before. So the blue dashed line shows the model calibration results from the week. And so definitely it's not perfect match. And also we can say some mismatch based on their peak flows and also the low flows, right? But unfortunately, this is probably one of the best model simulation results we can achieve. And in terms of the metrics, it's greater than 0.8, because this is for daily streamflow calibration. So normally, this is basically a very good model calibration, although they're not perfect. So in terms of the snow comparison, because we have also snow tell stations from the mountains, and we can find very good pattern match. Although there are some up and down, the overestimation or underestimation for the peak sway. And so, but in the end, we try to use a ratio, and this is basically trying to say the snow melt contribution for the to the total streamflow generation. And through this ratio, we found for their long-term trends, the weak model is basically is this is basically very encouraging results, applying physical-based model. Although the patterns, some years they have some mismatch, but overall trends is amazing. They are basically almost identical in terms of their long-term trend lines. So it's very exciting to see these results, because based on this model simulation, and especially based on their long-term trends, we can basically, study further for their different changes, variabilities, and in the hydrological regions, right? We also did the daily daily long-term trends and for the whole catchment. And we found in on May 1st there is significant increase, but on June 1st there is opposite trends, significant decrease trend. Also, we can find this through their spatial trend studies. And this means that during the melting period, there could be some major changes. So through the this is a comparison study between future study period and the baseline period in 1990s. So the major changes, it happened mainly in winter and spring because this makes sense, right? Because in this period, basically they have large snow accumulation and snow melt. So they are basically the major variability to affect the streamflow generation. So it's very clear now we can say from this time series comparison, and this basically the snow melt time series, and for the two different study period, base period the 1990s and 2050s, and we have two scenarios. So quite clear we can see this timing shift. And in 2050s, we found they have early snow melt in spring, but this is basically a lower snow melt peak in later spring. Basically, this is early summer. So this is quite interesting finding. Continually, we can find this from the streamflow simulation. And basically, the early melting is almost like 30 days, a big shift from 1990s to 2050s. But with a lower peak in 2050s, almost like 20% reduction for the flood peak. And so another major issue, ecological issue, is generated because the lower stream flow in summer. This can result in huge impacts on salmon migration during this season, and this can definitely a potential issue and generated from our study. And also in terms of their spatial distribution, we found this basically part of the mountain regions. This is basically the Rocky Mountains. And we found that the contribution in terms of the ratio is down from 0.7, 0.8 in 1990s to 0.6, 0.5 in 2050s. So this can maybe it can reveal major phase change in term precipitation, right? In terms of the snow contribution, so maybe more snow transition to rainfall in 2050s. So this could result in huge impact on the stream flow regions, right? So through this model introduction and case study, we found the current major challenges in traditional hydrological models. So definitely we have something we cannot figure out in a short time frame. For example, the scaling issue and especially the upscaling issue, right? And also the uncertainties in the model structures and generated by the model calibration and this parameter matching process. So all this basically it can generate large uncertainties, bring more risks for our studies. But before this, the new pathways, basically that's the mainstream for in hydrology, and especially for hydrological forecasting, we have to rely on. So next part, I want to throw a comparison, and basically this is a case study, two case studies, and ongoing research project in my research team. So we use data-driven models trying to improve forecasting for both floods and droughts. This research project is funded by British Council. We focus on the Mekong River Basin. The full name basically is now called Lancang and Mekong River Basin, origins from Qinghai province in China and also flowing into 6 countries. Especially this is basically called Mother River for Southeast Asia. So I have 2 field trips I have visited with the team to visit the major sport of the river catchment. So that's definitely an amazing experience. So used to be Mekong River Basin is a troublemaker. It's very important for this area because it's the major water resources for these countries. But meanwhile, it's used to be a troublemaker. For example, in 2009, this high intensity precipitation in 3 days bring these huge issues for Vietnam, especially the middle part of Vietnam, resulting in huge loss of people and loss of the damage of the properties, especially for agriculture. More than 1,000 square kilometers they were damaged. And also, this is basically from the handbook of provided by MRC, Mekong River Commission. So we have some kind of like collaboration in terms of the model development. So this is basically the traditional benchmark. Used to be we have a numerical weather focusing model and coupled with a hydrological model or plus with hydrodynamic models. So through this framework, we can generate basically the major metrics parameters for the flood inundations like area, depths, or even velocities. But now we have a new pathway we're trying to explore using AI. And so this is made by my postdoc and trying to make it more clear in terms of AI, the relation between AI, machine learning, and deep learning. So our traditional impression about AI, just like a black box, right? So we give the input and say the output, but not exactly to know what's the exactly process in this box. But my postdoc work is trying to make it more transparent. So this is the motivation for Dr. Yang Chiu working on this project. Uh, but at this stage, she focused on the lower Mekong River Basin and trying to test different parameters, land surface conditions. And also this is trying to categorize them into 2 categories, dynamic and static variables. And you test the different deep learning algorithms and to say which one would be best, most suitable, and for this model runs. And she tested this using 2 test bands, although in the paper manuscript, we have done all the work for these 8 basins, excluding for the delta, because this different story. So for this model runs, we also did the weak model simulation. And in terms of metrics, the best calibration results we can achieve is about 0.75, and some even less, for some areas. But for these 2 catchments, 2 subbasins, basically it's about 0.74 or 0.75. So it's reasonable because this is basically for daily streamflow calibration. But the amazing thing is once she used this data-driven model, especially using LSTM, and she can achieve much better model runs in terms of this evaluation metrics. It's easier to get model simulation about 0.8, some even better than 0.9. And for basin 5, it's even much better. So definitely we have other research outcomes, but here I just want to show you for in terms of model sim calibration and what's the advantage generated from the data-driven models. For the drought study, this work it was done by one of my PhD student. So actually he focused on this delta areas because this is basically in the past several decades, the delta area actually they suffer more droughts instead of floods. Given, because since 2008, I think there are more than 1,000, even 1,500 hydro dams they were built up, in the whole river catchment. So that's the reason why Delta now it's changing the hydrological issues. It's more droughts instead of more floods. So he applied this LST9. This is a combination of deep learning framework and using CNN, RN, and FC layers. And because they cover different, we use this for different purposes. So there are some, also he did this model comparisons with the physical base model, regional climate model, and we can say large great advantages and through these model comparisons. And also, this is actually basically a surprising thing when he tried to, investigate the relative importance for this land atmosphere variables and which variable actually it can generate more high impacts on these major key variables between the land atmosphere interactions. And surprisingly, he found that, all these relationships we found through this study, it can provide more insights into the underlying physical processes. Means that there are more in line with the research findings from the physical based models. So it shows great model capacities. And also through these studies, and this all the results generated from the uh, deep learning based framework. And he found that basically for uh, sensible heat in the dry season, because this is basically the dry season and wet season, and it can affect the precipitation generation, have a reduction of 20% precipitation. And for soil moisture, they have huge impacts for both dry and wet periods and about the precipitation formation. So I think I don't want to go deeper in terms of the detailed research findings, but through this, I want to say this is basically capable help us to identify what the physical base model they can reach. So in summary, basically through my own research, uh, the research we have ongoing research project in my research team, and also through other studies, we we want to generate this conclusion. AI basically can be a game changer, and also the great advantage because they can address some these challenges, traditional challenges in our traditional hydrological models. For example, the upscaling issues. So, but they are not perfect. We have to uh, confess this, because they are data-driven models. So for some areas, if there are not enough data, probably there are some issues. And also in terms of the initial cost, basically the time you have to invest to study the AI-driven models, but through the experience of my postdoc and PhD student, so I would like to say this is pretty much reasonable relative to some complicated land surface hydrological models. So here I would like to stop here to take any questions, and thank you very much.
Hello. Thank you. Thank you very much, John. It was stuck my computer a bit. Now it's the time for questions. Thank you, John. It was like very informative, even though that I'm not coming from this topic, You generate my curiosity for 3 questions, but I will provide the floor to the audience first for any questions. I will provide the floor to Shmuel. Please, Shmuel, the floor is yours.
Thank you very much. Very interesting and insightful presentation. And I want to ask you a question. If according to your opinion, governments and authorities need support development AI solutions for hydroclimatic extremes.
Okay, so thank you for your question. I just want to confirm your question. You're asking basically from the perspective of more governance side, right? So what can be generated, especially focus on the economical benefits. I'm not sure this is I got your question correctly.
Yeah, thank you very much.
Okay, all right. So I think that so far, in terms of AI-driven models, and it's very popular. And as I just mentioned at the beginning of the talk, it's not great interest in academia, but also in industry. I think also for other stakeholders like policymakers in the government, and I can give you one example. And I think it's back to uh, 2019, we organized a workshop in Glasgow. We invited some colleagues from Met Office in the UK. And at the time, I introduced this idea because at the time I have applied some research funds from British Council and NERC with the topic of AI-driven models. So at the time, I asked this, I think he's a communication manager. So whether or not the Meta Office they consider to develop AI-driven models, but the answer is no. But luckily, through the recent contact, they are working on this. So that's I think from the different stakeholders they have realized the potential for AI-driven models. I think this definitely I cannot say more about the potential benefits, right? Because everyone is trying to apply AI in their subject areas, including different stakeholders. Yeah.
So, George.
Hi, George.
Yeah, George, the floor is yours.
Yeah. So, John, thank you very much. Very interesting talk. And you're right, AI is taking over. I hope it doesn't take over all our jobs, but but it is indeed something very, very special that is happening now. So in our chair, we use it for flood forecasting, but of inundation extents. So you are on the hydrological side, we are more on the hydraulic side. So flood inundation extents with time, also looking at velocities, water depths. And one thing I got curious when you were talking about your experience with AI is that you saw this jump on improvement from you mentioned 0.7 I think, and then 0.8 and even larger than 0.9. And I was wondering how much danger is there that you're going into this range of overfitting of your model, because it becomes suspicious if it's very close to 1.
Okay, this is a very good question, George. Actually, we noticed this, during the model, model implementation, and I think we try to avoid this, but sometimes it's suspicious, as you just mentioned. Once it's going up to over, even I saw the results is close above 0.095. This is basically mission impossible for physics-based models. Definitely, there are some issues for the overfitting. I think, but I think unfortunately, we are not getting involved with the AI model development itself, So that's the motivation for me trying to develop a further collaboration with some colleagues from computer science. Yeah, we are trying to say because from their end they don't know exactly our needs. So I try to working with my colleague in computer science, we are trying to say what's the best from their side what the best could be technical support for us to develop this flood forecasting algorithm to avoid all the issues, especially including overfitting issues. Yeah. Yeah, that we noticed this issue. Yeah. Thank you.
Yes, I agree with you. It is sometimes we have the need to go to our you know experts in AI that then really develop them and so on. Although I still think it's maybe even more valuable to keep an eye on our colleagues in hydrology and hydraulics because there is a lot of knowledge there which we can use to better train our models. And this is something we experience here at University of Zigano when we are working with AI models. But a lot of the knowledge we had from the past, we can actually bring into the AI. And this is completely knowledge which is not aware by the people developing those methods.
Yeah.
So it's a
Yeah,
win-win
I fully
situation.
agree. And also, I think the next step we are trying to do is not fully relying on one single model. Actually, we are trying to combine traditional hydrological models with AI data-driven models. I think it turns out this basically to combine to avoid the issues for either models. Yeah, that's great. Thank you. Thank you very much.
So thank you, George, for your question, and John for your response. You gave me an idea. I think that the next thing that we're going to organize from September, since Ilka is here, Ilka, please keep a note this for our next meeting, like an AI seminar for students, AI fundamentals, how to use and applications. And definitely George and John, you're going to be invited to give your perception, to our students, to ourselves. Because it's very much
Great.
important. Here I have my fourth question. I will start with my fourth question because of the question of George, but probably it's a naive question. So, George mentioned about overfitting, all right? But I will say, like in the prediction model, if you over supply data from the past, however relevant is, because for the climate change, I don't know how relevant is the models in the past and how well they can predict. But let's say that they can predict. If you train your machine learning so heavy with so many elements, it should approach one, no? You should have, this fitting, no? John, what is your opinion? But this probably is a naive question. So the more data you place, the closer the prediction should be to the reality. Otherwise, it's going to be a useless prediction model, no?
Yeah, that's a very good question. Actually, that's also the work my postdoc was working on and trying to change different input data and including because there are basically more than 36 parameters. So she is trying to say using different parameter combinations and then to test the results and to tell the difference. And I don't want to say give you a yes or no answer because this is really up to the parameter combinations and different combination can generate results. Sometimes, just maybe very least parameter setting can generate very good results. And sometimes, more parameters may be misleading the data-driven process. So, but sometimes maybe it's opposite, So I don't want to say, okay, more data fitting into the data-driven model, it can generate maybe opposite effects. But I would like to say it's data in terms of the nature of the model. It's a data-driven model, right? It turns out more data would be better for them in terms of the model training and testing. But what's the turning point? What's the difference?
John, let me do now my third question. I'm starting from the opposite. I mean, one of the things about the prediction models, of course, is the prediction. The management is the management. However, what I was very much impressed from the first experiment of AI in MIT about cancer, it was like, the models, they provided also solutions. So this out of the box, combination of the existing knowledge also it could be useful for solutions of the problem, not only to predict the problem, not only to manage the data during the problem, but also, what kind of suggestions do they provide? Have you ever checked, you or George, since I can understand that you are coming from similar area, or at least you are using also the similar tools. I mean, have you trained your models, AI models, also to suggest solutions?
Well, not directly, because we basically George can understand this
We
better
can
as
start this
hydrology,
Athena Talk School
because
now.
we
All
feed the
right.
data and generate data. But I would like to say this is still a tool, although it's very popular. Or sometimes some people say this is magic. But I would like to say AI is still, as the nature of the tool, it's used by people.
Yes, yes.
So we still use it. It's not like a magic stuff, we fully trust. It's still a tool. We need to place it as the role of tool instead of, our God, right?
But sometimes, this is the power of the computation. This is the power of the big data. I mean, you need to trust, you need to build the culture, because then how are we going to use AI? Now we are returning back to the higher education people. They say, well, should we trust AI? AI is a devil. No, AI is a tool, is an application that we should live together. So we should build the culture in order to trust AI, and by critical thinking, try to apply. For example, in cancer, they trust it, and they provided the treatment of the specific cancer in MIT. For example, in the other case, AI models, they propose to F-35 pilots, for some maneuvers that the pilots they don't trust to do it. So I mean, we need to create the culture also to somehow to trust critically. And I don't know,
Yeah.
George, if your models, AI models, also provide suggestion of solutions.
It's a good question. Let me see. Sebastian, are you there? Sebastian is my PhD student.
Excellent. Let's engage Sebastian.
Yeah,
Another
I'm here.
another
Hello.
speaker for our future
Hi.
action. I will keep the notes, Sebastian.
Sebastian.
So actually, our AI models make a forecast, and the suggestions is what we want to derive. So actually, it's our job as a scientific researcher to, yeah, to derive to look at the results and make suggestions, because we are an expert in the end. So because we use inundation models also to forecast inundation, and so we see what our AI model is resulting in is it's an inundation map. So what we see is what is inundated, and the suggestions afterward is what we need to look at. So
Okay.
actually not yet.
Not yet. Okay, so we have plenty of space to
I want to
reach the
underline
Americans.
more. It's really up to, because AI itself, they don't know exactly the physical meaning for this data input to the model, right? And the same for the outputs. So it's really up to us how to address this, how to interpret this, right? So like for the data, Sebastian just make the prediction, and really up to Sebastian how to address this properly. But for a researcher in from like in Costas, your research area, probably they have different explanation, right? So
I don't know. I'm coming from laser physics, so we don't use
okay.
AI, right now, how to make, laser systems. But I would like to about the transparency that Sebastian, you, and other people they are talking about. From the moment that you develop the algorithms, from the moment that you control the algorithms. I mean, I cannot. I mean, what are you doing? I mean, it's not a black box. I mean, even and this is a problem with AI. You're biasing. Probably it's going to create through the algorithms, and not very inclusive, let's say, prediction. I mean, this is not a question. This is an observation that I'm doing from outside. That if you develop the algorithms, somehow you bias the system somehow, because the system, combines in a different way out of the box that probably the human mind cannot realize. Yes, George?
Yeah, actually, in the work from Sebastian, he's going a bit further. He's saying, I'm not going to provide one map of flood inundation, but I'm going to provide a probability if it's going to be inundated or not. So to get a bit away of that uncertainty, which is coming from many sources, we don't know where. So we are looking to this as well.
Yeah. Probably we can play some quantum mechanics then. They are here. The probability, you can be there or you can be other ways. And in this case, you are safe.
It's more safe to use the probability.
All right. Before we finish, I would like to share you a small video in order to celebrate, the last talk of this year. And, this is something that, the Athena communication have developed. So I hope that you can see my screen in order, to close and renew. Oh, come on. All right. My computer. I don't know. You cannot share. You cannot listen my. All right. Just a moment, because I did not share the sound. So this is like to show you that this year, this is the 5th year of the Athena talk. This year, 33 talks with an experts from all over the place, from all of the technology. I would like to encourage all of you, George, Sebastian. You are going to be contacted to be part of this community for the next. So with this, I would like to thank you for your participation, for your engagement. As I said, John, last but not least, and we're going to renew our meeting and our sessions from October. You are going to be informed also from Ilka. Probably, George, we will come for a podcast to your laboratory, in July, that we will be, me and my colleague George in Zigen, in order to discuss about your research. I'm sorry. The dog would like to go out. And thank you. Thank you very much, and see you soon. Bye.
Costa,
And thank you very much for inviting me.
Bye-bye.
Just a moment. George Kavoulakis would like
Costa, on behalf of all of us, we should thank you and George Kavoulakis for your effort. One small one this year, during the whole year. We are grateful to both of you. Thanks a lot. And thanks to the speaker, of course, also.
all the speakers. Yes.
Okay, thank you.
George?
Thank you too.
All right.
We will come stronger in few months.
All right.
We will come back.
See you soon.
Bye.
Bye-bye.
Thank you.
Bye. Bye-bye, everyone.
Bye.
Bye. Bye.